I'd like to introduce Andrea Mock, a senior at Wellesley College, who has been doing active research with IMD with Professor Volich. Andrea, are you actually in the US right now, or are you overseas?
I'm currently in Germany.
You're currently in Germany, and it still looks bright outside through your windows. So welcome. Andrea will be speaking about political structures and topological data analysis.
Thank you for the introduction. Hello, everyone. Today I will be presenting on political structures and the topology of simplicial complexes. This is work that I have done jointly with Professor Volich at Wellesley College. And if you've ever heard the term topology in the mathematical context, the first thing that comes to mind is probably not something related to politics, since topology is really a very abstract branch of mathematics. However, topology is being used in different areas of study, and what really motivated this research is previous research done by two political scientists, Abdu and Keating, who wrote a paper on how topology can be combined with the notion of political structures. So what we wanted to do was kind of build on their work and try to exploit the structure of simplicial complexes as a way to model political structures, as well as use certain constructions on simplicial complexes to model interactions and other phenomena in political structures. And because topology is not a topic that most encounter in their daily lives, I will first give a brief overview of what simplicial complexes are, as well as what can be done with them. So a basic definition of a simplicial complex is that a simplicial complex consists of a set called V, whose elements are called vertices, and a set of subsets, which is called delta, where all the vertices themselves have to be subsets. And if you see a subset in delta, you will also have to see all of its subsets as well. So to make this a bit more clear, let's take a look at a brief example of a simplicial complex. So we try to represent a simplicial complex by this graphical representation. And here we see that the vertex set is made up of 7 vertices. And an element of delta is a simplex, and they are geometrically realized as vertices, edges, triangles, tetrahedrons. So for example, here we can see V7, and this is just the vertex. We also have V3, V5, this is an edge, and then if you look at the realization here, we can see that it's this edge, for example. Right. And some other useful definitions related to simplicial complex is this notion of a maximal simplex. And that is basically a simplex that is not a face of another simplex. So in this example here, we would say that V1, V0, V3, and V2 is a maximal simplex because it's not contained in anything else. But on the other hand, V1, V2, V3, this bottom triangle here, is not a maximal simplex because it's contained in our tetrahedron. And we say that a vertex is dominated by another vertex if every maximal simplex that contains that particular vertex also contains that of the other vertex. So if we take a look at our example here, we would say that V0 is dominated by V2. And lastly, the star of a vertex is a subset that consists of all the simplices that have this vertex as a face. So if we take again the vertex V0, we say that the star of it is just everything that is like emanating out of it. So what I just marked here. And now that we've introduced like this basic definitions, we can also do different constructions on simplicial complexes. And one of these is the wedge. So the wedge is basically the merging of two simplicial complexes. We have here K and L, and the wedge is basically obtained as the union of K and L. So here we have two disjoint simplicial complexes, and then we see on the right that there is a joined simplicial complex. And this here we call the wedge point, so the point that joins these two complexes. Next, we'll take a look at the cone. And so the cone is basically obtained by having our simplicial complex here and adding a vertex and connecting all of the vertices in our simplicial complex to this point. And so here we say that C is our cone point. And I can briefly demonstrate this here. If we say this is C, I just connect all of my vertices to this point. And by doing so, I get the figure on the right. And so the cone is an example of expanding our simplicial complex, adding some things. And you can also do the opposite and delete a vertex from a simplicial complex. And the deletion is basically removing the start of a vertex. And the deletion of a dominated vertex is called an elementary strong collapse. And it's denoted by this here. And this is just basically saying we have our simplicial complex K and we remove a vertex V. So it's no longer contained in our simplicial complex. And a sequence of elementary strong collapses is just called a collapse. So we can also take a brief look at an example here showing these different elementary strong collapses. So if we look at the very top right left corner, we see our simplicial complex, and if we look at V0, we see that V0 is dominated by V1, V2, and V3. And so if we delete V0, we take its star, which is this here, and remove all of that. So in the second picture here, we see that V0 and its star is no longer contained. Similarly, now our starting point being the second picture, we see that V1 is dominated by V2 and V3. So we remove its star, which is just this here, and we get the picture on the right here. And this process can be repeated as often as you like. And here we just see a sequence of elementary strong collapses, and then we end up with V3, V4, V5 at the very end. And so to end off the section on simplicial complexes and topology, let's just briefly introduce the notion of homology. So homologies basically counts the number of n-dimensional holes of a simplicial complex. So to each simplicial complex, one can associate a sequence of groups called homology groups, one for each nth dimensional group. Each of these groups encodes the number of n-dimensional holes in the simplicial complex, and it's denoted by NHK here. And so if we look at this example here, we say that the zeroth dimensional homology is basically the number of zeroth dimensional holes. And here we say that H0 is Z, so it's trivial because we only have one simplicial complex. If we had another point here that is part of our simplicial complex, our simplicial complex would be disjoint. So there'd be two parts of the simplicial complex. And each one basically denotes the number of one-dimensional holes in our simplicial complex. And here we see these are, there's two of these. So that's why we have Z squared, because of these two holes. And similarly, H2 is Z, so there's one two-dimensional hole if we consider this tetrahedron and we say that it's not filled in, so the inside is hollow. So that's our two-dimensional hole. So now we've covered quite a few definitions and examples. So let's actually finally move on to the actual looking at political structures and how these notions of simplicial complexes can be combined. So a political structure we define as P with a set of agents. So agents can really be anything. They can be voters, political parties, jurors, members of a legislative body, etc. And a subset of agents is a viable configuration if the agents are compatible, i.e. they're willing to negotiate or compromise, or they agree on an issue or a set of issues. And having a viable configuration means that a system can continue to function. So by just looking at this definition, we can see that there are already some parallels to simplicial complexes. Basically, our agents in political structure are vertices in a simplicial complex, and the viable configurations we just talked about are the simplices in a simplicial complex. Since we mentioned agents can be pretty much anything, political parties, countries, etc., let's take a look at a brief real-world example that is based off of Middle Eastern politics. So this political structure represents Middle Eastern countries and different political parties, and this information about the relationships was gathered from an article from 2004, so it's important to state that things might have changed since then, and obviously this kind of mapping can be done for other countries or other political parties of voters, etc. So taking this as our baseline, if we say we look at agent 5 and agent 3, agent 3 is Saudi Arabia and agent 5 is Egypt, what we can see is that there's no direct connection between these two. So that just means that Saudi Arabia and Egypt don't talk to each other. So they're not really willing to negotiate or enter a coalition. As a counterexample to that, we can see that there's this triangle here. So A6, A4, and A9, these three. So here we have Hezbollah, Iran, and Syria. They are willing to communicate with one another. They're willing to enter a coalition. And at the very extreme, we have these two agents that are not related to anything. So this is Al-Qaeda and ISIS, and they don't really have any relationship to any other political party in this political structure. And so similarly to many of the definitions introduced for simplicial complexes, there's also parallel definitions that can be established for political structure. So we say an agent is dominated by another agent if all of the largest possible coalitions that include all of these also are part of the other agent's coalition groups. So we say that one agent is better positioned in the political structure if it dominates the other agent. And we say that therefore this agent is more central in the political system. Similarly, again, this notion of the star. The star of an agent is the collection of its compatibilities. So the collection of all the potential coalitions an agent is willing to enter. And finally, as introduced earlier, the deletion of an agent is the removal of all the simplices that include this agent as a vertex. And that means that agent no longer is present in any political coalition. So this kind of also motivates two notions of viability and stability. So if an agent is part of a more viable configuration, they are more viably located in a political structure. And that means that a lot of good things can happen. There's dialogue between the agents. And so we also talk about this notion of viability. And here we see that the viability is defined in terms of the star of an agent. So the star of an agent, again, if we remember back to our example, it was basically everything emanating out of a vertex, or here out of an agent, all of its connections. So the viability kind of increases if there's more connections. And all of these other terms that you see, the 1 divided by 2k minus 1, are just normalizing factors to have the viability be something between 0 and 1. And similarly, the stability is defined as this huge term here, and this might look a bit daunting, but most of these terms, this here and this here, are just for normalization. So that the stability of a political structure is also something that is between 0 and 1. And basically the stability tells us how many simplices or how many subset of configurations there are in our political structure. So if P, our political structure, has lots of simplices, then lots of coalitions are possible, and P is more stable. So we've also defined two further ideas, the notion of merging and mediating. So this picture might already seem kind of familiar from earlier. It's basically showing what we introduce as the when. So say we have two political structures and say they decide to join or merge. And this happens often in a political landscape. Two parties decide to work together. So that is basically what is considered merging. And this, again, as I said, is just the when. So here we see these two political structures, and then they merge. They have some issue that they agree on, and this is here, this merge, this wedge point, as we called it earlier, that is used to merge that. And so again, if the viability of an agent that merges increases by this merging process. And so again, the stability is also increased when when agents merge if they are disconnected, like here in this example. So next, let's talk about mediating. So a mediator is basically an extra point or an extra agent that is willing to join in a coalition with other subsets of agents. So this picture also might seem familiar from earlier, and this is basically this notion of the cone. So the mediator is really just willing to enter a coalition with any subset of agents. And again, the mediator, by having this kind of friendly relationship with all other parties, increases the stability of political structure. There's more kind of dialogue going on. And so if we go back to this initial example of political structures and Middle East, we see, like we said earlier, there are these two lone agents, Al-Qaeda and ISIS, and say we introduced a new actor, another country, and then would have connected all of these together, then this would obviously be a mediator that kind of helps dialogue increase between all of these parties. And this obviously can be done for other examples. And so there's many different things that can still be done with this notion of political structures in simplicial complexes. And here are a few other possible future directions that this work can take. One of them is the refinement of weights and their meaning and how this can be used in political structure. So for example, there's parties and a party has 5 votes, and then they decide to enter a coalition. How would you represent the total number of votes or people in these two parties that are entering a coalition? That is something that could be done with weights. And another idea that could be further explored is this collapsing of subcomplexes as a way of showing how power is delegated or how compromises are created, and maybe also bringing in ideas from probability, signal processing, which have already used different ways of using simplicial complexes in a very unique way. So that was it from my side. Thank you so much for listening. And if there are any questions, feel free to ask now.
Thank you very much, Andrea. As a topologist, I really appreciate your talk. It's actually very fascinating that you can do this. Are you writing a thesis, or is this an independent research project with Professor Volage?
This was an independent research project.
Uh-huh. And are you writing that into a paper that we can all read someday?
Yeah, so the paper is actually already on ArchiveX online, and we submitted it to a journal, so you can find it
Wonderful.
online.
Yeah, so I should mention, I mean, we'll get to, I should mention that if anybody would like to offer their, I think the speakers would like to offer a transcript of their slides for our other audience members, we would very much welcome it. So are there any questions for Andrea?
Yeah,
So,
I have a question.
Go ahead.
Yeah, so is there, why might, what are consequences might you be able to draw about actual political systems? I mean, it's really, it's fascinating because this notion of coalitions is really how things get done. But I wonder, you know, if I were able to draw a map of some political system that I'm familiar with, what kind of insights might I draw from the topological analysis that would help me in my political quest, whatever it might be?
I guess one thing that could be interesting for like political parties is to see where their coalitions are, what topics they kind of align with one another. And the interesting thing is that we were able to compute these like holes that I talked about using computational software. So you could easily write up your simplicial complexes, like how your parties are related to one another, and see where, I guess, there's more space to find a coalition. So it could be used for political parties in the future to maybe see what issues they want to focus on or who they want to create a coalition with. It's like a better mapping of who's out there, basically.
If I can maybe augment that answer, sorry, Andrea, but you could, so you could plug in your simplicial complex that models your political system into a simple sort of homology calculation software, and it'll tell you where the homology is. Having a non-trivial homology means that you can't have certain coalitions, right? You have holes, and it'll tell you more than that, like what subsets of agents will not enter a coalition, and then you can then strategically place mediators into substructures to mediate. So you're basically capping off homology classes and sort of making them trivial. That's what introducing a targeted mediator into a substructure might be. So that's the kind of thing that this might tell you. I mean, how practical any of this is, obviously.
Ismar, are there ways, for example, of identifying, the linchpin, the most sort of to identify various, entities in this graph as being the superlative of something, right? So, the most willing to talk, the most influential, and then perhaps the graph might tell you, well, if this person doesn't work out, who is the next best person to ask? Yeah. I mean, or find some kind of gradient, like, movement inside. I don't know if these things can be captured homologically, but these are, important things that people use graph theory for.
Yeah, I think so. In combination with this notion of stability and viability, which are really sort of very, very sort of, they just count the number of simplices. They're not terribly exciting, right? But still, they seem to be capturing something about political structure. I think that, the viability of an agent in combination with knowing which sort of non-trivial chains in homology it belongs in, I think it sort of can tell you how you can sort of most efficiently introduce compromises into political systems, something like that. I don't know. Yeah, there's lots that can be done with this thing.
I just realized that, you might be hearing a thumping noise from behind me because my neighbors have decided to to have a party. But are there any other questions for Andrea?
Andrea, Abbas asked a similar question to what I'm going to ask in the chat, which is sort of the introduction of time and how these political structures might change over time and the simplicial complex would change. And there are like mathematical tools to sort of detect how homology responds to these sorts of changes. I'm curious if you've graphed out any of that or if you have any of that in your paper.
So I think we kind of include like the basic notion of collapses. So how you get from like a simplicial complex to a different simplicial complex over time. But I don't think we haven't really said like, okay, this is T0 and this is like T10. So we just include this like very basic notion of, okay, there's like this iterative process that is happening.
Cool, thanks.
And if I can butt in again, sorry, Stanley, feel free to shut me up.
That's fine. We have some time.
But there are these like evolutionary simplicial complexes, right? And there's, I think, homology that can be associated to that sort of time series simplicial complexes. There are sort of evolutionary voting models that are modeled by simplicial complexes as well. So I'd like to sort of borrow and steal from all those notions and import them into this idea of political structures. But yes, there's something, and there should be something done for time parameter evolution of a simplicial complex, and work on that exists, but I don't know much about it.
Smart, by the way, are there journal? I mean, you've submitted this for publication. Are there journals that specialize in, intersection between pure mathematics and these kinds of, social systems?
So actually, Jonathan, I think Hodge in the morning talk mentioned a couple. One of them was mathematical social sciences. That's where we submitted this paper. And then he mentioned another one that I wasn't familiar with. So maybe if he's still around, he might answer this. I know Stephanie has also been looking into these journals. Theory and Decision. Okay, thank you. Yes, there it is in the chat. But there's at least a couple of these. And then there's sort of, like if you're doing like topological data analysis and gerrymandering, right? So there are topology journals that'll consider those papers.
I mean, it would be interesting.
Yeah.
Not that anybody has any time these days, but it would be kind of a fun exercise for a subset of us to maybe get together over the summer and read some of these articles to see what kinds of publications are actually coming out, because this is an area about which I know very, very little, and what is interesting to people and what is publishable. So I mean, if that's something that interests you, I'll make that as an option in our sort of survey after the conference. Yeah. Well, thank you again, Andrea. That was a wonderful talk. Let's thank her again. And we have